So, it's been almost a year since I first started exploring how we can use deep learning to generate game graphics. And I made a video about the same showing how Grand Theft Auto 5 graphics can be synthesized by a neural network. A year later, today seems like a good time to make a follow-up video and see what new research papers have come out since and how much improvement has been made in this time. So if you guys are ready, let's get started. About a couple of years back, NVIDIA published a research paper for picture-to-picture conversion where they introduced the pix-to-pix network. It can be used to render realistic looking graphics by using the semantic maps like shown here. While the results looked very promising, there were still some shortcomings in terms of the desired output. First major issue was that the output was very low resolution and the synthesized images lacked a lot of fine details. But since then, NVIDIA has managed to improve the quality of its AI massively. The researchers came up with a follow-up paper that ported the pix-to-pix algorithm to work for videos as well. This algorithm, named vid-to-vid, short for video-to-video translation, massively improved upon the output quality and also reduced the flickering between frames that we see in the pix-to-pix output. To understand how this paper improved upon the original pix-to-pix GAN implementation, let's take a look at its generator. It uses not only the current semantic map that we want to convert, but also few semantic maps from the previous frames. Additionally, it uses the final synthesized frames from its previous output and combines these together to compute a flow map. This provides the information required to understand the difference between two consecutive frames, and is therefore able to synthesize temporally consistent images. On the discriminator side, it uses an image discriminator like in pix-to-pix to control the quality of output, and in addition to that, it also uses a video discriminator to ensure that the frame-by-frame sequence of the synthesized images makes sense according to the flow maps. This ensures that there is very little flickering between the frames. On top of this, it employs a progressive growth approach that starts with first perfecting low resolution outputs, and using that knowledge, it progressively moves up to produce higher resolution outputs. Now, I must admit, the output quality of this network is really impressive, but there's still one practical problem that comes up if we actually want to use this AI in a game. If you have noticed, games like Grand Theft Auto have a day and night cycle, as well as weather effects like rain and fog that completely change the appearance of the virtual world in the game. If we want to make a vid-to-vid network render graphics for all these different scenarios, we will have to train separate network instances, one for each visual effect. So this is quite impractical to use for the game developers. But what if there was a way to train a single neural network to be able to learn all of these different visual effects, be it day or night or rain or anything? Wouldn't that be great? This is how I came across this very interesting and creative paper that came out recently. Rather than focusing on improving the quality of the output frame, it focuses on being able to synthesize diverse images from the exact same semantic map. This means we can have the same scene rendered in any lighting or weather condition using this method, unlike with GANs, where one semantic label can only produce one output. This paper shows how to use implicit maximum likelihood estimation or IMLE in order to achieve this. Let's try to understand why IMLE seems to work better than GANs for this use case. With GANs, the training process often suffers from the problem of mode collapse. Imagine a bunch of training images in some higher dimensional coordinate space, which we simply represent here in 2 dimensions. Some of these points represent daytime samples and some represent nighttime images. Now, when we start training an unconditional GAN, we first generate a bunch of random images that will be pushed through the generator. Now, the training process essentially tries to push these fake images towards the training images so that they look real. This leads to a problem where some of the training images may be left out and never be used. This will lead the generator to only produce images of the same kind as training goes on further. Hence, GANs suffer from mode collapse, and images generated by this method cannot be diverse in nature. So let's look at how the maximum likelihood estimation process tries to address this problem. It first picks a training image and then tries to pull a randomly generated image close to it. This is the opposite of how it works in GANs. Next, it picks another training image and pulls another random image towards it. This process is repeated until we have covered all the training samples. This means our training process now covers all day and nighttime images, and thus our generator is forcefully trained to produce diverse style of images. Now, note that this is the unconditional case of IMLE, where we start from a random noise image rather than a semantic label map. But the training process remains the same for both cases. The only thing that changes is the input encoding when we use semantic maps. So let's take a look at that. Now, instead of using an RGB image as input, we break down the map into multiple channels. Each channel corresponds to one object type in the map. Now, here comes the most important part of this paper, which I personally found the most interesting. It uses an additional noise input channel to control how the output style looks like. So, for one random image in this channel, the output will follow a fixed style like, say, daytime effect. If we change this channel to some other random image, it will follow another style like maybe nighttime effect. And by interpolating between these two random images, we can actually control the time of the day in the synthesized image. This is really cool and fascinating to me. I tried out this method on a footage of GTA 5 just to visualize how it would look like. So I took a short video and used a segmentation network to derive the semantic label maps. And sure enough, after running it through the IMLE based network, the output I got was amazing. Remember that both the daytime and nighttime images are generated here by the exact same network, and that is truly amazing. Now, there is some flickering between the frames, but that is coming from the imperfect semantic maps I obtained with the segmentation network and not due to this algorithm. So overall, I really like where this research is going. Combining the two papers we saw today, vid-to-vid and IMLE based image synthesis, we can truly see how far we have come in AI based graphics rendering. There are only a few more hurdles we need to clear before we start seeing games using this new AI based graphics approach. Now, you guys might be wondering why AI rendered graphics is such a big deal if the current graphics tech is already doing a great job. Well, here's the problem. Games like Grand Theft Auto, they require almost 10 to 15 years to design and develop. But with AI, it is possible to design these massive open virtual world games in a fraction of that time and also at much cheaper costs. And this is the reason why I am so excited to see more and more research papers come out in this field. What do you guys think? Are you excited about this AI technology? Do you think we'll see something like this in Grand Theft Auto 6 Or do you think it's too early for that, but maybe in Grand Theft Auto 7? Let me know in the comments down below. And I'll catch you guys in the next one.